Thank you, Kyle. So good afternoon, everyone. My name is Samir, and along with Ankit, today we would like to take you to the journey of scaling Spark at Facebook. In particular, this talk, we are going to focus on three aspects. We are going to discuss some hardware trends that basically influence some of our design decisions and how we look at scaling Spark at scale. Then we are going to talk about certain optimizations that we have added in the Facebook engine over time. And then finally, we are going to talk about our users and their use cases. So just a brief introduction about us. I'm a software engineer at Facebook in the data warehouse team. I'm an Apache Spark committer where most of my work has focused on Spark Core and Spark SQL. And previously, I spent many wonderful years at Databricks and at UC Berkeley AMP Lab, where a lot of my work has focused on building large-scale distributed databases and distributed systems.
Good afternoon, everyone. My name is Ankit. I'm a production engineering manager in the data warehouse team. I have been at Facebook and in the data infra team for 7 years. For the longest time, I was a Hive user at Facebook, and I never thought we'll actually move away from Hive. So Spark has been a very interesting journey for us. And before that, I was part of the search team at Yahoo, and we were one of the first teams using Hadoop at that time.
So here's a brief agenda for the talk. In the first part of the talk, we'll start off by taking you to a journey of how Spark came about at Facebook. Then we are going to talk about some hardware trends. As I mentioned, like hardware trends and more generally the way CPU disks and memory is evolving plays a very important role in how we actually think about tuning Spark and actually scaling Spark on clusters of tens of thousands of machines. Then we are going to talk about some specific optimizations that we have added or some specific themes of things that we are doing in Spark around history-based tuning and join optimizations in the core Spark engine. And then, essentially, we'll take a deep dive into our users and how they are using Spark in production. And finally, conclude by giving you a sneak preview of the vision of how Facebook thinks of large-scale data analytics in a time frame of 2 to 5 years. All right. So to really understand the role of Spark at Facebook, it's really important to understand the role of data at Facebook. Now, this should not come as a surprise, but the data that our users share with us effectively underpins and plays a very important role in how we build our products. This data not only allows us to better understand our users and actually show them relevant content, it is actually also allowing us to do a lot more. Things like A/B testing frameworks, things like fighting spammers or fighting fake news is something that's very dependent on essentially this data and the complex analysis that we do as a result of it. And at Facebook scale, this actually requires a platform that can actually scale in all aspects, and Spark is essentially that platform for Facebook. Now, combine the complex applications that I talk about with just the fact that there is enormous data that we have to process. Between the Facebook family of apps, when we're talking about Facebook, Messenger, Instagram, and WhatsApp, we effectively have 2.7 billion monthly active users and 2 billion daily active users. And what this means is it basically presents some amazing scale challenges for the data warehouse team, and Spark is essentially at the center of all these challenges. Now, Spark has had a very humble beginning at Facebook. It basically started off at 4 years ago as an experiment in 2015. And fast forward to today, in 2009, it's actually the biggest compute engine at Facebook by CPU. We actually run some of the world's largest Spark clusters in this world. And essentially, we are effectively doing complex analytics that actually spans jobs that range between like hundreds of thousands of tasks, shuffling petabytes of data, running on tens of thousands of machines. OK, so now let's actually motivate the rest of my talk by actually like talking about certain hardware trends and how Facebook actually looks at optimizing Spark in this constraint space. Now, when we talk about hardware, we are effectively most interested in three aspects. We want to know how CPU is evolving, how RAMs are evolving, and how our disks are evolving. Now, if you look at the industry trend in case of cores or CPU cores, we see that the industry is now increasingly optimizing for adding more and more cores. And essentially, in order to optimize the performance per watt, which is performance per unit of power, the next generation processors that are coming into the market effectively have more cores, but they each run at a smaller frequency. In terms of RAM, we see a very, very interesting trend. The price of DRAM, if we are looking at like essentially a horizon of like the last 3 to 4 years, have been actually fluctuating a lot. So if you look at things in the time frame of 2016 to 2018, we see that the prices of RAM have almost increased by 3 times. And the last year had been very interesting, where the price of RAM suddenly starts dropping by 30 to 40%. Now, what this means when Facebook actually tries to kind of like buy hardware and tries to kind of like basically populate data centers is that whenever we do capacity planning and whenever we actually factor in the cost of our resources, and RAM in this particular case, it's very difficult to actually predict the future. It's very difficult to actually like do capacity management and capacity planning if like the price of RAM is fluctuating so much. So all in all, we are trying to actually build software, and Spark in particular, that actually reduces our over-dependence on RAM. So I just need to be clear that we are not actually proposing a world in which like Spark would actually operate on less and less RAM. We just don't want to over-provision RAM if there is not a good reason. Third, this should not come as a surprise, but the disk sizes continue to increase year over year, but the number of random accesses that we have are not actually increasing. So in our clusters and data centers, what we are seeing is that instead of storage being a bottleneck, IOPS, or the IO per second, actually becomes a bottleneck. So combine all these three trends, what does it really mean for Spark? So I talked about CPU, where each processor now has more cores that run at a lower frequency. I talked about RAM, in which like essentially the price volatility in the market actually is kind of like basically getting us into a direction that we would want to reduce our over-dependence. And then I talked about IOPS becoming a bottleneck. So one of the things that we are actually seeing is pretty obvious from the first two trends, which says that if my cores are increasing and my memory is decreasing, we would like to actually optimize Spark for an increasing core by memory ratio. The next generation of machines that we are going to buy would increasingly have essentially more cores and lower memory. Second, given that IOPS is now a bottleneck, Facebook actually starts to run disaggregated compute storage clusters. So we cannot actually do this traditional shared nothing architecture in which like you basically share the same machine for storage and compute, but we want to actually disaggregate them so that we have one compute cluster and one storage cluster, and so such that we can actually scale and upgrade them independently depending on whatever resource becomes the bottleneck. So in case like our compute becomes a bottleneck, we can always buy more optimized machines on the compute side, but if IOPS, or essentially storage, becomes a bottleneck, we can scale our storage clusters independently. The other kind of like advantage of this is that we can also use server types that are more optimized for compute and storage. So a compute cluster would actually have servers that have more cores, probably more RAM, but a storage cluster would have basically like machines that probably have flash, might have like a lot of disk, possibly like less amount of memory and other things. And the third kind of like observation, which is a bit obvious in this context, is that we are basically now buying hardware every year, or if not more, and essentially we now have this problem of scaling Spark with all its diverse set of workloads across these clusters of tens of thousands of heterogeneous machines. So the machine that I buy today would be different than the machine I buy tomorrow and the day after. So essentially, we would like to actually build and scale Spark such that it can scale on these heterogeneous machines without any problems. Now, what does Spark architecture look like in this design space? So first of all, as I mentioned, we are running Spark in a disagged world, which means that all the Spark executors are actually running on a compute cluster, and the storage, whenever Spark reads and writes data, it spills, it shuffles, it basically happens on a separate storage cluster. Both these clusters can be scaled independently depending on whatever is the bottleneck. As far as the compute side is concerned, we actually run a wide variety of heterogeneous nodes. So basically, our clusters, depending on the machine life cycle, which can range from 0 to 5 years, can actually comprise of a distinct set or a heterogeneous set of machines at any point of time. And we have built schedulers that can actually scale to these tens of thousands of machines or heterogeneous machines, and which can support Spark well. Now, the focus of my talk would mostly be on the core engine. I would mostly be talking about how we are running Spark on the compute side of things. But the other two problems that I talked about, basically making Spark work in a disagged fashion and actually designing a scheduler that can scale to heterogeneous machines is equally interesting. So I'd actually just like to put in a forward pointer to two very interesting talks by my friends at Facebook that actually talk about Costco, which is an efficient Facebook scale shuffle service, which happens today at 4:30. And then we're talking about Tangram, which is this distributed scheduler for Spark at Facebook, tomorrow at 11:50 a.m. All right, so we talked about some hardware trends. Now the question is, how are we actually leveraging these hardware trends in evolving our core engine? Now, over many years, over the last 4 years, Facebook has contributed more than 100 plus patches upstream, kind of like dealing with every aspect of scalability, possibly bug fixes, new features, and so on and so forth. In this talk, I'll not actually go and talk about all of these patches or all of these individual things, but I would like to actually give you some intuition on the theme of work that we are actually looking at and how kind of like these optimizations govern that. So first of all, we are actually looking at history-based tuning. So now in a world in which like essentially we are trying to scale Spark on heterogeneous machines and on a diverse set of workload, one config that kind of like basically is operating on a cluster level does not actually do the job. We would like to actually tune Spark on a per job and per stage basis, and I'll try to motivate this problem like a little bit later. And then the second thing is, in a disagged world, joins are crazy expensive. They kill you because every time you're spilling or every time you're actually shuffling huge amounts of data, you're actually paying much more cost than essentially something that would actually you would incur when you only spill or shuffle data on disk. So what this means is we have actually invested a lot of effort in going beyond the 3 standard joins in Spark and actually creating a range of hybrid versions of these joins that actually leverage some of these levers or trade-offs in this design space. So let's talk about both of these one by one. Now, talking about history-based tuning, the high-level idea or kind of like the whole idea behind or motivation behind this problem can be actually traced to this graph. So here I have like essentially our cluster utilization. This is one of the biggest Spark clusters at Facebook, and we are looking at essentially 1 week of memory utilization for that cluster. Now you see 3 lines here, right? These are very interesting lines. The bottom line is essentially the P50 memory utilization, which means that 50% of our machines are actually utilizing, depending on the time of the day, 10 to 60% of memory. 5% of our machines are utilizing somewhere between 55 to 70% of our memory. And some of the heaviest Spark queries and some of our heaviest machines are actually taking or basically utilizing 80 to 100% of the memory. What this actually shows us is that any one-size-fits-all config, so let's say that I basically tune all my jobs and or my cluster and kind of like draw a line anywhere in this graph, is going to basically underutilize resources for everything that's below it. If I draw this line too high, it is actually going to underutilize resources. If I draw this line too low, it's actually going to affect all the jobs that actually needed more memory. A slightly different but kind of like complementary way of looking at this is to actually look at the task memory usage that we can actually monitor in Spark. So Spark has accumulators for monitoring the peak memory usage. And when we look at all our production data and try to basically compute a CDF, that basically plots the amount of memory that's used by every task, we see this kind of like realization in which that 75% of Spark tasks that we execute in production, and by the way, this could basically range from hundreds of thousands to millions of data points per day, we see that these tasks are actually using less than 600 MB of execution memory. This should not come as a surprise because essentially tasks that are just scanning things or basically they're not doing fancy aggregations or hash maps or joins would actually not use too much memory. They are just basically going to buffer a very small amount of data. Tasks that are doing massive joins or computing hash maps or doing aggregation are much more likely to consume memory. But all in all, this means that, again, if I am actually allocating the same amount of memory to every Spark task, it is actually not going to work out well. Which means that this individual resource requirement per task has a huge variance. And again, like this actually means that we need to tune Spark on a per job and a per stage basis. So in order to actually make it work, we heavily are considering to leverage historical characteristics of a job to actually tune configurations. Some examples of this include, we want to look at the peak execution memory, the graph that I just showed, and the spill sizes for historical jobs to actually tune the off-heap executor memory for the new jobs. We also want to look at the shuffle sizes, the amount of data a job shuffles, to optionally not insert partial aggregates or insert it depending on a case-by-case basis. We also want to basically look at the shuffle sizes in this instance of probably the input data size to actually predict the number of shuffle partitions that we would like to do on a per stage or a per job level. Now the list goes on, and I don't want to actually like discuss each and every case, but the high-level point here is that we would like to actually tune our jobs by looking at characteristics that are unique to the historical run of the job. Now how does it work? It basically works in the way that whenever we see a query, we actually compute the query plan template for that query. Now, for those of you who are familiar with like essentially the Spark code base, this query plan template just extends the base query plan class. And what it does is it basically strips off the data-dependent aspects from the plan. So in this particular case, even if my query is operating on different partitions of data every day, I don't actually keep that, or kind of like basically I abstract that from the plan, so that this query plan template can actually be compared across different runs of the query. Now, when we see this query plan template, we look it up in a database that we have for historical job runs. This database contains weeks and weeks worth of data, and it helps us tune basically new runs. Now, if that corresponding query plan is found in the database, we find out if there are any regressions in any of the past n days of like this query. And if they are not, we actually leverage many of these rules that I just talked about to actually apply these config overrides. Now, once we apply these config overrides, we execute the new query with the optimized set of configs. And now two things could happen. Maybe what we did was right, and it actually did optimize the query. We'll have a positive feedback loop in the database. But if we did not, and if we ended up making a wrong choice, we actually would go back and basically do this feedback loop again, look this up for a subsequent query, and then look for regressions. So in case my query regressed historically, we can always go back and apply conservative defaults to our queries such that the next run of the query does not regress or does not fail. So this was the historical tuning part of things. Joins, as I said, are also extremely expensive in a DSAG environment, and we have basically spent a lot of time and energy in optimizing that. So Spark traditionally has three kinds of joins, and this is basically very common for every database, actually. We have the broadcast join. The way broadcast join works is that you broadcast the small table to all the nodes, and then you stream the larger table. The advantage of broadcast joins is that it's skew resistant, but the disadvantage obviously is that this table that you need to kind of like broadcast need to be small enough to be able to fit in memory. Then we have the shuffle hash join, which essentially is a slightly better version of like a broadcast hash join. What it does is it can shuffle both the sides, but then it has to create a hash map for a smaller tables partition, and then stream the large table partitions and does a hash map lookup. So it's slower than broadcast joins, but it actually can handle much more bigger tables. The third variant of joins are basically sort merge joins. The idea behind sort merge joins is that you shuffle and sort both the tables. You buffer one side, and you basically stream the other side. So in terms of memory profile, like sort merge joins are much more memory efficient because you're not creating these fancy hash tables or actually keeping things in memory. But then, I mean, given this, you incur this additional cost of sorting the data, they are slightly slower. Now, we actually worked on three variants of these joins to actually like tune cases that kind of like fall into these cracks or somewhere in the middle. So one of the things, especially for people like who have worked on Hive, Hive has this notion of a sort merge bucket or an SMB join. So the way bucketing works in Hive is that it allows you to shuffle and optionally sort the output data that's being written by a table based on certain columns. And the key idea behind this is that essentially if you're writing something once and reading it a lot of times, the sort merge join that actually shuffles and sorts this input data every time does not have to actually incur that cost. You can just basically sort it once, shuffle it once, write it down, and then you can actually just read it back without incurring that cost. So this was basically the idea behind the SMB join. It's just a variant of sort merge join in Spark. And it basically overrides, in the planner, we override the output partitioning and output ordering of basically the Hive table scan exec operator such that it can read the bucketing information or the sorting information from this metadata or from this partitioning metadata. And then it actually just stitches all this partitioning ordering information throughout the query plan. So sort merge join, when it actually incurs or actually joins the data, it already finds out that the data is already sorted and shuffled, and it just basically avoids this whole step altogether. The other variant of these two joins that we actually discuss is called dynamic join. Dynamic join is based on a very famous paper by David Devitt and Norton that kind of like is a hybrid join algorithm where each task starts off by just doing a shuffle hash join. So this is the second join I talked about, which is there in Spark. But in the process of execution, if the hash table that we have on the right ooms due to some reason, we actually go back and automatically reconstruct this hash table. And if we cannot, it just basically falls back by sorting it to a sort merge join. So it's basically a hybrid between a shuffle hash and a sort merge join, where some tasks can do the sorting and some tasks will actually have to do the shuffle hash join. A third, but a quick variant of essentially these joins is a skew join in Spark, which basically is a hybrid join algorithm that processes skewed keys via broadcast joins, which is skew resistant, and the non-skewed keys via shuffle hash join. So the way it works is we basically allow users to add hints on these plans, on these queries, and once we find out that a certain key or a certain column has a skew, we can actually just create a planner rule to split this into two joins. So all in all, I talked about three things. I gave you an overview of how Spark is currently being used at Facebook. We talked about a few hardware trends that actually give you an overview of this design space or this optimization space that we look at. We talked briefly into some of the ways how we are evolving the core engine, specifically around history-based tuning and join optimizations. And next, Ankit has actually give you a deep dive into how our users are actually using Spark in production.
Thank you, Samir. Hello, everyone. So when we talk about our users and our use cases, it's first important to understand who our users are, who's using Spark at Facebook. Now, when we did this exercise, it was a bit surprising to us as well, because this keeps changing. So the first bucket of people using Spark at Facebook are data scientists. These are people who have strong algorithm background. They actually are able to do deep analysis of the data that's available and draw meaningful insights. They usually don't necessarily have a software engineering background, but they have analytics background. The second set of people are data engineers that account for 15% of our users. And these are the people who have deep understanding of query optimization. They're building these frameworks that can run these critical workloads to do these large query plans, which are complex, have multiple stages, but are able to do that efficiently. But the biggest bucket of users that we have are actually software engineers. These are the people who do not have SQL background, that's not their primary responsibility. But they do it as part of their daily job. For example, an engineer in Instagram trying to figure out what impact a feature they have rolled out may have on the end user latency. Or somebody in the feed team trying to figure out a change in feed algorithm what kind of impact it has on how users are interacting with the feed. Now, these kind of cases, software engineers are working through every day, and what that highlights is that unless we build our system that is simple to use, that is easy to use, that actually users that is simple enough to use, they will actually struggle. They will not have a good experience. And when you think about having thousands of people running hundreds of thousands of queries every single day, automation is the key here. So one aspect that we have the one way we have handled this is by automatic error classification. Now, error classification itself is not a new concept. Every system that can have any kind of failures will want to do error classification in an effective way. But there are a few ways to think about it. The first way is system errors versus user errors. User errors are errors we think are caused by a user-induced problem. It could be a semantic exception, analysis exception, that user can take an action and fix. But the system errors are the more interesting ones, because that is where Spark as a system can do a better job. These could be transient failures. For example, if metastore is unavailable transiently, or there is a storage error that we see. And in most of these cases, a retry would actually fix the problem. And we want to make sure that we are doing this well so that the system can do the retry and does not loop in the user, reducing the cost of a human coming in and actually fixing the problem. But retriability comes at a cost. You can't blindly retry. If we know the system is down for hours, we can't just keep retrying this query and wasting compute on those resources. So understanding the root cause of why a failure happened becomes a really important part. And doing this, again, automatically and accurately is a key aspect of how we think about error classification and build that into the system itself, into Spark itself. The second part is even when we see user errors and we expect users to be able to fix that problem, that will only happen if they see a message that they can actually act on. So one of the things we have done is relatively simple, but it allows users to give feedback on the error messages that they are seeing. And by analyzing the data around what kind of error messages we are showing and whether users feel they're able to use that efficiently or not, we can decide which parts to focus on, which areas to things to fix to improve the user experience. So this is around how we think of our users and how we kind of make things better for, again, thousands of users running these queries. But going to the next aspect of how we think of our use cases is what kind of queries are being run at on Spark. So the diversity of the workload itself. We look at it from query count and CPU. If you look at the query count, the biggest chunk of the queries, and not surprisingly, is pure SQL. These are SQL queries that mostly our software engineers are writing to actually process, to do just simple analysis. But actually, there's a big chunk of workload that is also SQL, but it leverages custom UDFs or transform scripts, which are custom code that's running as part of a SQL to transform your data. And the smallest chunk there is actually data frame-based queries, which actually account for only 1% of the number of queries, but do account for a larger share in CPU. Now, the reason I share this is understanding how our system is being used goes a long way into how we build new features, how we think about new features, how we think about testing these features. Because every decision that we make around what features we are building and what kind of impact they might have on the end user needs to be based on this information. Now, standardized testing here is an approach that everybody takes. So you have a user, you have an engineer on the team building a feature. They use standardized tests. It could be TPCDS, TPCDH, or something else that you've come up with. And you log these metrics, you evaluate that, and you kind of use that as a feedback loop to figure out whether it's expected, the changes are expected or not. Now, standardized tests are great because they have predictability into it. You can actually compare previous runs to the next runs and actually see if there's any problem going on. And it works great if your workload is static. It doesn't work if your workload is continuously evolving, which is the case we see. So comes in shadow testing. So the loop is kind of the same, except we have plugged in shadow testing instead of standardized testing. Now, shadow testing is a way to play back queries from production in an isolated environment that allows you to do two things. One, make sure that your results are correct, so there are no correctness problems. And the second is to check performance and make sure that there are no performance regressions or anything like that. So you're actually seeing the expected changes for the particular feature that you're building. Now, to make this even more effective, we have introduced a concept of tags. So suppose you're building a new feature like dynamic join. There's only a certain query shapes to which it applies. And if you tag all the queries that actually match that query shape, you can actually use that when you even pick queries from production and actually make sure that your shadow testing gives you the right coverage and the right insights into your feature, into your change you're making. Now, this basically just improves the quality of the code you're putting out, the changes that you're making, and gives you high confidence in the changes you're making. And we actually use it in a bunch of use cases. The first one is, of course, when you're building new features, but also for our regular releases. So at Facebook, we release Spark once a week, sometimes more often. And the reason we are able to do that is we have very high confidence in our testing strategy, because we know what kind of impact it will have, and if there is a regression, we'll catch it. Our automated testing will catch it. But it can also be used for configuration updates that you want to apply to a subset of queries, right? You can actually test those kind of changes as well, actually run through the same system. And even for hardware testing, when we have a new set of hardware and we want to compare a query running on the old hardware versus the new hardware, what kind of changes it might have, we can use the same framework as well. So this actually greatly improves not just the developer efficiency, but the end user experience and handles evolving workload. So we talked about two things, right? So we talked about who our users are and what kind of workload they are running. But the third aspect of the workload that's running on Spark is what criticality of the workload is. So not all workload running on Spark is equal. There's a workload that is actually used for defining the top-line metrics or engagement metrics that actually we need to know on time every single day. At the same time, there are pipelines, a workload that's running every single day again that is used for something, a specific feature or something experimental, right? Those cannot have the same priority as the jobs that are publishing these top-line metrics. Now, to enable that, we actually schedule our workload using different scheduling algorithms. So Fastlane is the workload where that's the most critical workload that's coming in. We want to make sure anything that comes in gets completed as soon as possible. So we use a FIFO scheduling algorithm there. Same time, we have pipelines, which are these regularly scheduled pipelines, but we want to make sure that we are where latency is not the top priority, but throughput is. So we use DRF, which allows us to improve the efficiency of the cluster, the throughput of the cluster, at some cost to latency. And then we have use cases like backfill and interactive, where user experience is the most important thing. And using user fair share is the right strategy there. Now, having this understanding of the workload and actually building these scheduling algorithms based on that is a big part of how we think of building these features into Spark. Now, this is all great. This is all great for the user experience. But there's one thing that we have to do for our sanity as well, which is building defensive deployment as part of the Spark itself. And these are the guardrails that we put, not just for us, but for our users as well. Things like hard limits on config values. We don't want users to set like crazy values for the amount of memory they want to allocate to executors, because that can affect other jobs running on the same machine, or launch millions of tasks and cause overall resource shortage. We also want to make sure that we have good capacity quotas, so to make sure that the storage and compute resources are being used efficiently and effectively. And the third is strict resource limits or containerization, to make sure that when we have a single machine running different workloads, they don't kind of step on each other's toes. And I'll talk about the last one, because that's a very interesting use case. So for resource limits, we use cgroups at Facebook. And if you think about a Spark executor running on a machine, we put it in a cgroup, in a cgroup, and we focus on CPU and memory as the key resources that we control using that cgroup. And on a single machine, there are multiple of these executors running, so it's important for us to make sure they don't interfere with each other, or if one misbehaves, it doesn't affect the others. Now, while CPU is an interesting thing here, I'm going to focus on memory, because that has raised some very interesting challenges for us. So this is what an actual configuration on our host looks like, right? For each of our executors, we set the cgroup limit to 12 gigs. But the overall limit that we set on the container, on the root container, is actually 40 gigs here. So if you do the math, we're actually doing oversubscription. The reason is that actually statistical multiplexing actually works in this case, because at any point of time, not all of them are going to use all the memory allocated to it. And we saw, when you looked at the history-based tuning stuff, we saw that that's actually the case. So it's actually a great way to kind of make sure we are able to control the resource utilization, but also provide efficiency. And if you look at a CPU and I hope you can see that well. But if you look at the CPU and memory chart for a cluster, you can see it actually pretty good. Like CPU utilization is high, memory utilization is fairly static. We're actually getting good throughput on the cluster. But then something went wrong. We started seeing a drop in CPU utilization on this cluster, and didn't see much change on the memory. And it was unclear to us why this is happening. Our first thought was that this is happening because the workload running has changed. But that was not the case. Because while we were looking at these two resources, there was a third resource at play, which is I/O. What it showed is when we saw the CPU utilization drop down, the disk I utilization had shot up. Now, this was a mystery, because we actually don't have swap enabled on our machines, because that was the first thing that came to mind, that, hey, maybe the host is swapping. But it's not the case. We don't even have swap enabled on our machines. So what really was happening? Well, while we were doing the setup, there was actually another setting that was sneaked in, which was memory.high. So if you read the documentation on memory.high and memory.max, memory.high is a way to put memory pressure on your processes and actually evict pages from memory so that your process doesn't get killed. Because once you hit memory.max, the only option is for the killer to come and kill your process. So this memory high and memory max zone gives you a place where memory pressure will be applied, and if your process behaves well, it'll actually come down into the normal zone, and you don't have to kill the process, you're still able to make the progress. But what happens if you make a mistake in the configuration? What if the memory.high and memory.max values differ a lot? Now, this is what happens. A process starts, and as soon as it hits the memory.high limit, it stays in that mode, and it's continuously thrashing. So continuously hitting page faults, these binaries that your process is using continuously get flushed to disk and get read back again, and flushed to disk and read back again. And that causes the I utilization, because every major page fault will result in an I/O. Now, this was an interesting problem, because we thought Cgroup was a solution, but actually posed another problem. Because what happened is our Cgroup configuration was wrong. So it raised an interesting problem about how we think about configuring these systems can actually make some of these things detrimental to the system itself. The other interesting thing was why it happened. And it happened because of history-based scheduling. So we added history-based scheduling to tweak the memory setting at the executor level so that we are actually doing this more efficiently. We thought we are adding efficiency to the system by actually tweaking the memory setting correctly. But what ended up happening is it actually made it worse. So takeaways from this was Cgroup configuration can be tricky. Finding the right balance between efficiency and reliability is really important. And a bonus was, well, we need better resource controls on I/O as well, because that's a resource that we haven't thought about. Now, this is all very interesting. This is all that we have done. But Samir said 2019 is when we are starting to scale Spark. So the road ahead is even more interesting. Scaling Spark continues to be a challenge. We're going to continue scaling that 10x, 20x over the next few years. The other interesting thing is redefining warehouse itself. Warehouse, for the longest time at Facebook, was a collection of services and tools that our users could use to do analytics. In true warehouse concept, it needs to be unified. Concepts like columnar storage or bucketing needs to be inherent into the warehouse itself and not something that the users need to care about. And the third is going beyond SQL. SQL is still the biggest use case at Spark. We think ML, microbatches, they're all great opportunities for us to kind of embrace and make Spark even more interesting at Facebook. With that, I don't know if we have time for questions. I think we have 2 minutes. But yeah, thank you.
Time for 1 or 2 questions. So if there's a question, I'm sure Samir and Ankit can meet you in the back. For those exiting, please exit on the left. We're going to have people come in on the right. So my left, your right. Please exit that way. And remember to download the app and rate the sessions. It'll help make future Spark Summits better. So with that, I'll let one question go. Thank you.
Hi, this is Good Talk. I want to know what's kind of like average query latency that you guys expect from the clusters and like the query latency.
Query latency?
Yeah.
So to repeat the question is like what sort of latency they expect from the cluster.
So you're talking about the average query latency at Facebook? So we do, right? I mean, I don't have the exact number with me, but I can give you an intuition in which, like, essentially 80% of our queries actually are not doing shuffles. So essentially, the latency, if you look at the median latency, is actually like less than 5 minutes. But if you look at the average latency, like it's always kind of like influenced by elephants. Like 20% of our queries are extremely huge. They're shuffling petabytes of data. So average latency, again, like, I mean, I apologize for not actually having the exact number, but I would not expect
yeah, but
it, I would expect it to be in hours.
Like yeah, what do you expect? Like most queries don't take a lot of CPU, and they run a lot shorter, but there's a small set of queries that actually take a lot of resources and actually end up running for long durations.
I see. Thank you.
Yes, let's do that.
Yeah, so if any others have questions, Samir and Ankit will be in the hallway for further questions. We have to get ready for the next session. Thank you.